tungsten, which has the element symbol W on the periodic table, has 5 naturally abundant isotopes: W180, percent abundance 0.12, W182, percent abundance 26.50, W183, percent abundance 14.31, W184, percent abundance 30.64, and W186, percent abundance 28.43%. Part A, how many protons and neutrons would be found in each isotope's nucleus? Part B, explain how the percent abundance of each isotope would have been obtained. Part C, draw the mass spectrum, percent abundance versus mass for this element. And Part D, write the shorthand electron configuration for this element. If you haven't tried these parts already, try them on your own now or with a group, and then we will go over each part together. Okay, Part A asks how many protons and neutrons would be found in each isotope's nucleus. So first of all, in order to be the element tungsten or a tungsten nucleus, all isotopes have to have 74 protons. It is element number 74 on the periodic table. Then to find the neutrons, we just have to take these mass numbers that were given, 180, 182, 183, 184, 186. Remember, those are the total protons plus neutrons. So if we subtract the number of protons from the mass number, that will give us the number of neutrons. So I've taken each of my isotope mass numbers, 180, 182, 183, 184, 186, subtracted 74 to get the number of neutrons for each isotope, 106, 108, 109, 110, and 112. Part B asks, explain how the percent abundance of each isotope would have been obtained. So how did we get these percentages here? This 0.12, 26.5, 14.31, 30.64, 28.43. How do we get those numbers? Let's think about what we're studying in this unit, right? We're studying mass spectrometry and electromagnetic radiation. So we can find percent abundance using a mass spectrometer. Percent abundance would have been found using a mass spectrometer to ionize samples of tungsten and determine the relative abundance of each mass to charge ratio of ionized fragments in the sample. Shown above in an intensity, signal intensity versus mass graph, the most abundant isotope is recorded with an intensity value of 100, and all others are shown relative to that value. All right, so in Part C, we want to draw not the signal intensity versus atomic mass spectrum. We want to draw the percent abundance versus mass spectrum. So we are given the mass and the percent abundance for 5 isotopes. So we can draw a graph that shows each of these 5 masses on the x-axis and each of these percentages on the y-axis. And that's what we have here. The 180 is the smallest, 0.12%. Even this is probably a little big, but we had to show it, right? 182 is a little more than halfway between 20 and 30. 184 is right there about 30. 186 is just below it, and then this 183, 14.31, is between 10 and 20. Okay, so that's how we can draw a mass spectrum showing percent abundance versus mass number. Finally, in Part D, we're asked to write the shorthand electron configuration for this element. So we have to find tungsten on the periodic table first. And we know where it is because we've determined the number of protons already to be 74, right? So it's number 74 on the periodic table. It's W. Okay, and so the shorthand configuration, remember, starts with the noble gas in the previous row or the previous period, which is xenon, Xe, right? So xenon. Then what comes after 54 is 55, right? And that's in the 6th period. 1, 2, 3, 4, 5, 6. I'm counting on my periodic table. That's the S block. So we would write 6s2, but we're not going to do that. We'll talk about why in a minute. 6s1, 4f14, 5d5. Now this is tricky, right? Your initial instinct might have been to write xenon, 6s2, 5f14, 4, f14, 5d4, right? Why isn't that correct? We have to remember that our electrons want to be in the lowest energy levels possible and most stable energy levels possible. And an almost half full D subshell is not very energetically stable. Okay, but a half full D subshell, which would be D5, is energetically stable. So what happens is one of these S electrons jumps. Remember that those energy levels are really, really tightly packed and close together at those higher levels. So it's not like a huge jump there. So one of those S electrons jumps, and we end up with one of these exceptions to that rule that we've written electron configurations before, and we get 6s1, 4f14, 5d5.